All right, let me get going. All right, so tolerancing. What is tolerancing? That's what we're going to talk about and learn in this chapter this time. So if you take a look at the cover sheet here, you can see some very cool looking chains and gears there. Those are actually made at Sandia National Laboratories, based on a design that one of my students did years ago when I used to teach technicians how to design in very small scales. Okay. So those gear teeth are about 8 to 10 microns in width. And the chain links are about 10 or 11 microns from link to link. Okay, so that's pretty small. 100 microns is the width of a human hair. Okay, so you can imagine the tolerancing for making these things is very, very tight, right? So that's an example of where you would need very high level of tolerancing. Okay, all right, let me continue on. So I already mentioned Chapter 5 homework on sectioning is due soon and posted. Let me know if you have any questions or have difficulty getting it done in time. You can go ahead and do that. Mr. Fernandez, you've got your microphone on, so if you could go ahead and turn your microphone off, I'd appreciate that. Thank you. All right, let's continue on. So think about what tolerancing means, and maybe in your notebook or something, kind of write down a couple of things of what you think tolerancing is and what it's for. Okay, I'll give you a minute or two to kind of think about it. And if you have something to share about what tolerancing means, you can go ahead and put it in the chat box. Okay, no one's got any ideas? All right. So what it is you're going to be dimensioning. You already learned how to dimension things, but you want to dimension things in such a way that you can interchange parts. Okay, so interchangeability allows you to manufacture things and be able to put them together with interchangeable parts. Bit of trivia. Does anybody know who invented the assembly line and interchangeability of parts? Who's credited for that? Harrison Ford? No. Everybody's thinking Henry Ford. Well, he moved it along. It was somebody before Henry Ford. Ah, Trenton, you got it. Eli Whitney. Good job. So Eli Whitney was the one who wanted to get a contract from the government back in the 1800s to make not cotton gins, but to make rifles. So if you can make rifles, and good, Anna, you got that right. You said guns. Yep, absolutely. So in order to make a large quantity of rifles, you'd want all the parts interchangeable. So that way, when the soldier's on the field and his gun fails, they can exchange out the failing part. They can make them in mass production. But before Eli Whitney got into this business, all the guns were custom made. So, you know, there were muskets and things like that. So they were each made by hand and custom made. So if a part broke, you generally had to take it to a gunsmith and they would fabricate a custom part for that. Okay, so interchangeability of a part is simply making it so it can be mass produced. So you can have replacement parts. Okay. So here's one way to specify tolerance for dimension. So you can write it as is given in this slide. So here the tolerance is 0.994 to 1.005. So if you make your part and that part ranges within those limits, you're good, okay? So what do you think the total range is? Does anybody want to venture? Putting it in the text box. It's 1.005 minus 0.994. That's the range. There you go. So Gabriel got that. 0.011. So that's the tolerance range you're allowed to have for whatever feature it is that we're discussing here. Okay. So those are the size limits. So if you make a part that's 0.994, it's still within tolerance. But if it's any smaller than that, it's out of tolerance. Okay. All right. So we have two limits that we typically specify when we're doing tolerancing, right? A lower limit and an upper limit. And these are called specification limits in industry. So that gives the person who's making it an idea of whether or not they made it right. Okay, so it's necessary to have two limits because it is impossible to manufacture parts without some variation. So you have to have a range. You can't tell people, I need it exactly 1 inch. There is no such thing as exact. And we talked about that in a couple of previous lectures, okay? So the limits give you an idea of what the quality control should look like. So the tighter the tolerances, the better measurement systems you need, right? So now your quality control measurement tools get more expensive, for example, or it might be more difficult to measure. So you only want to make tight tolerances when you really need them, okay? So you want to specify a tolerance with whatever degree of accuracy that's required for the design to work properly. So when you design things in SolidWorks, right, you can be very exacting because it's in a computer. So everything is exact, right? All your dimensions are exact. But you really want to design in some variation, right? Allowable variation, and that's where the tolerancing comes in. Okay, if you make the tolerance way too tight, then all of a sudden it's going to cost you a lot more, and it's going to be much more difficult to make. Okay. All right, we already saw that. All right, so let's take a look at this interesting slide here. This is showing two gear teeth meshing, and you'll take some classes later on where you talk about gears and transmissions and things like that. But the design of the gear teeth is really an interesting thing to go look into. So, you know, if you get bored at home, go ahead and Google gear teeth designs, and it's quite complex. Okay, so here's an example of two gear teeth, and you know, you look at it and say, well, what's the important tolerancing there? Well, some of it is the distance between the centers of the teeth, right? That's going to vary. So if the centers vary, you're going to have problems with meshing properly. So the center distance is real important. And then the base circle, the pitch circle, the hole depth, the addendum, the root, all of these things are specified. Okay, so making gears is something that's a really high level science. It's not even an art. It's very precise. So that's one of the hardest things to manufacture with high precision. Okay, so some gears don't need to be that high precision. All right, let's keep going here. So we've got pitch. So pitch is the distance from the same place on one tooth to the same place on the next tooth. Okay, and we'll talk about pitch some more when we talk about threads. Clearance is how much space you have available. Okay. Carlos is joining us. Center distance we mentioned, and shaft and holes, right? We're going to talk a lot about shaft and holes in this class, in this lecture. And shaft and holes will give you a really clear idea about tolerancing and how it all interacts. So stay tuned for that. So of course you want to think about what it is that you're designing and what the intent is. Of course, cost comes into play, how you're going to manufacture the part, right? And from your experience level and the experience of your teammates as to how tight of a tolerance you need. So some things need very high tolerances, others don't. So here's a close-up of that chain that I showed you in the first slide. And there you can see the different parts of the chain, a close-up of it. This is from a scanning electron microscope picture. Okay. And you can see that we've got thicknesses that are around 2 microns. So remember, 100 microns is how thick your hair is. So this is 1/50th of the width of a human hair. Okay, and then you have the shaft here. These are the links. They're connected through the shaft and up on top. It's kind of like a bicycle chain. Okay. So these aren't really machined like you would machine something in the machine shop. These are actually fabricated using the same processes we make computer chips with. Okay. And then when I was in semiconductor industry, one of the biggest things that we had to tolerance and specify were called CDs. CDs are critical dimensions. So you can see an example of a CD dimension with a tolerance of 1.1 micron plus or minus 0.1 micron. Okay, so that's about a plus or minus 10% or so. Nowadays they're making things as small as I think 14 nanometers, right, with tolerances of plus or minus 1 or 2 nanometers. Okay, so measuring things gets really critical. So when you're measuring these kind of small things, right, like a critical dimension when you're making microsystems or you're making semiconductors, you need a special tool for that. You can't just use a micrometer anymore. So there are optical systems, so you can magnify the image really big and then measure on the image, kind of like how you measure grain size, which you'll learn about next semester. In this case, we use a scanning electron microscope. So that uses an electron beam to image things. And then from that imaging, you can go ahead and measure the critical dimension. So you can see one scan of the electron beam going across the thing you're trying to measure. And you can see what the profile looks like. And then you can write computer algorithms to decide what that width is. So do you measure halfway up the rising edge or at the base and that sort of thing. So there's lots of algorithms and things engineers have developed to determine what the actual line profile is in reality and compare it to cross-sectional views and whatnot. So there's a lot of work involved in just doing quality control and measurement systems. So if you become an engineer and you're in charge of doing tolerancing and doing it accurately, you'll have the job title of metrology. So metrology is measurements, right? It's the ology of measurements, so it's called metrology. Okay, so we need a lot of standards when we're doing tolerancing. And of course, as we've learned in this semester, that standards are important so other people understand what we're doing. Okay, so if everybody does it the same way, writes it the same way, presents it the same way, then your manufacturers in other countries will be able to make the part correctly and repeatably. So there's a couple of different standards that are used. So the American National Standards Institute is ANSI. It's part of ASME, right? American Society for Mechanical Engineers. The International Standards Organization, also known as ISO, they have standards as well. And then there's micromachining standards on their own, and that's part of SEMI. So SEMI standards, which is Semiconductor Equipment Manufacturing International. So those are some of the more common standards institute. And then if you get into some really, like space applications or high performance engines, they'll have another set of standards that you need to follow. Okay. All right. So there are 3 tolerancing methods. You got limit dimensions. So you say what the lower limit and the upper limit is. So that's the first one. Or you can write it as plus or minuses. Okay, so you can write 1.00 plus or minus 0.10. Or you can do page and block tolerances. So those are the things that say, like, unless otherwise noted, right? Your tolerances are plus or minus whatever you decide as the designer. Okay, so limit dimensions. So here we go. This is a hole in a shaft, right? That's a common thing that engineers make. They want a shaft to fit in the hole, and they want it to either be a really tight fit or not so tight fit. And we'll go through that in a little while. But how do you write that? So there's an example below where you can write the diameter with the upper and lower limits, okay, on top of each other, or you can do them next to each other. And there's a standard for that. So if you do it as indicated on the left side, where you have the 1.001 above the 0.999, right? You want the higher number above the lower number, or the smaller number. Okay, and if you decide to write it out as indicated on the right side, then the lower number is on the left and the higher number is on the right. So that's a standard, right? If you do it backwards on your homework, or you present it in the wrong order, it'll be incorrect, and it won't be following standards. Okay, so that's just reiterating what I just said. So, what do you guys think? A couple of you try to answer this question. You don't all have to. Okay, it's not correct, right? And what about this one? Yeah, it is correct. Okay, the lower one's on the left. Okay. And then you can do plus or minus values as indicated here. Notice that they're not symmetric, right? You got a plus 0.1 or a minus 0.2. Now, this might seem weird, right? You're targeting 10, okay? But you can go a little bigger, or you can go a lot smaller, all right? So think about when you might want to do an asymmetric tolerance such as this, right? Does anybody think of a reason why you'd want to do that? Any ideas? Yeah, loose fit, for example. Very good. Or a hole. Yeah, there's certain cases where a hole you might want to dimension a hole this way. Okay, very good. All right, and then this is the other way to do tolerancing that we mentioned, is a block tolerance. So this is what it looks like. So take a look at that. And by the way, these slides are already posted, so you can flip through them later on as well. Okay, so shaft hole assemblies is something that we're going to talk about quite a bit in this lecture and in this unit. Okay. So take a look at this picture. This will be utilized over and over again. Okay, so you can see the hole, right? This is the hole. What's below the shaft has a range of 1.5 to 1.502. Now, the biggest the shaft can be, according to the way this is dimensioned, is 1.495. So if I make a shaft that's 1.495, it's still good, it's still in spec, right? And I make a hole that's 1.500, which is the smallest I'm allowed to make, you can see the shaft and the hole will match, right? The shaft will easily go into the hole, and it might be able to turn, and that might be something you want it to be able to do, right? So some things you have to realize is how do we dimension shafts and holes? And you can see how it's done here, right? You have the maximum diameter of the shaft and the minimum diameter, and that's indicated in the graphic on the left with a big D and a little d for the shaft. And that's the range it's allowed to be made in. Okay, so those are the ranges that are acceptable. Okay, and then on the right is the hole dimension. So you have the smallest the hole can be, little d, and the biggest the hole can be, big D. Okay. Oops. So inch tolerance definitions. All right. So the limits are the maximum and the minimum size that the part is allowed to be. So if it's outside of those limits, even a thousandth of an inch bigger than what you say it can be, it's scrap. Or you can maybe rework it. So if the shaft is too big, you can put it back on the lathe and take off a little bit of material, right? But if it's too small, well, you can't make it bigger. It's really hard to do that. Okay, so usually if a part is outside the limits, it's either scrapped, which means you lose money, or it's reworked, right, to get it within tolerance, but then again, you lose money. Okay, so basic size, so those are the limits, right, how big and how small. Basic size is what you're shooting for. Okay, so, you remember that previous tolerance, you had 10 plus 0.2 and minus 0.1, right? Or maybe it was the other way around. So that was an asymmetric tolerance, but you're really shooting for 10. That's the basic size, okay? So it's common for both the hole and the shaft to have the same basic size, right? So in other words, the basic size is the same for the shaft and hole. Okay, so if the hole basic size is 3, like in the example on the bottom of the page, and the shaft basic size will also be 3, typically, the limits for the hole might be 3.01 to 3.06, right? Notice that the basic size is outside of the limits, which is okay, okay? And then the limits for the shaft could be 2.95 to 3.0. Okay, and this will make more sense later as we get into more details on tolerancing. So the tolerance is really how much it can vary, and we call that spec limits. All right. Okay. So here we go. If you have a pencil and a paper, you might want to try to fill this in. So here we have a shaft. Okay, that's on the left side. You can see the diameter tolerance there. It's got the bigger one on top of the smaller one. And then on the right is the hole, right? And it has limits. So try to think of what the shaft limits are and the hole limits are, and what the basic size for both of them would be. Okay, and then the tolerance is the range. Okay, so let's go ahead and move ahead. So is this what you came up with for the limits? 0.47 to 0.51, and the hole would be 0.49 to 0.50. So hopefully you all thought of that. I wonder if you're all sleeping. Okay. And then the basic size is 0.5. And if you're working with inches, you might say ½ inch. Okay. All right. So the tolerance for the shaft. Can someone type that into the chat box, or a few of you? I'm going to look at these later and maybe give you some extra points if you're paying attention and contributing. Okay, would it be an issue to have the shaft with a higher limit than the hole? Could be. Okay. The tolerances for the shaft, okay, is the range the shaft can be. So that would be 0.04, wouldn't it? And then someone brought up the comment that if the shaft is bigger than the hole, what happens? Well, you might want it to be slightly bigger than the hole. And that's called a force fit. So if you're attaching a shaft maybe to a hammer head, right? The shaft needs to be, really tight. So you may force it in, and that's called a force fit. And then some of the older hammers, if you look at them, it's got a wooden handle and a metal head. They would force fit the shaft into it, and then they would actually put something in, plunge something in from the top to spread out and cause some more stress and tension so that that head wouldn't fall off. Okay. All right, so let's move on. Oh, the hole tolerance. Any guesses there? Yeah, 0.01. Okay, good. So tolerance is the range. The limits is how small you can make it to how big you can make it. And the basic size is the same for both, the shaft. So that kind of makes sense. I hope it makes sense to you. Think about it if it's not obvious. Okay. Now we're going to go into something called inch tolerance definitions, called maximum material condition, MMC, and least material condition, LMC. This is confusing for a lot of people. Okay. So MMC means when you have the most material. So when you have the most material on your shaft, is the diameter bigger or smaller than the least material condition? So you think of a shaft, okay, and it's in the maximum material condition. Is that diameter going to be bigger or smaller than that shaft being in the least material condition? It's going to be bigger, okay? Because the shaft that has the most material is going to be the one with the bigger diameter. Does that make sense? Okay. And now let's think about a hole. When a hole is in its maximum material condition, is the hole going to be bigger or smaller than when it's in its least material condition? Right, the hole will be smaller, right? Because as the hole gets smaller, that means you have more material. Okay, so it's kind of flip side, right? When you're thinking the holes and when you're thinking the shafts. So think about which has the most material and which has the least material and what that hole will be. Because there's some generic specifications and standards that are based on MMC and LMCs. Okay, so let's take a look at this. Look at the shaft. Which number would be the MMC? Type in a number. All right, Corey got it right first. He was first up, so 0.51. All right, what about the least material condition for the shaft? Which one would that be? All right, and the hole, the least material condition for the hole? least material condition for the hole. .5, right? We're looking at the hole, which is on the right side. So when it's 0.5, you have less material than when it's at 0.49, right? So 0.5 is the least material condition for the hole. One way to think about it is you drill a bigger hole and then you weigh the thing that you drilled a hole in. It's going to be lighter, right? Okay. So we did that. So let's fill it in. So that's the answer to all of those when you fill it in. So the least material condition for the shaft is when the shaft is the thinnest. And the least material condition for the hole is when the hole is the biggest it can be. Okay. Whoops. All right, here we go. Maximum clearance. Now we're going to talk about the material conditions and maximum clearance. So we're going to use the same example, which is in the lower right. So the shaft can range from 0.47 to 0.51. And the hole can range from 0.49 to 0.50. Okay. So when is it the maximum clearance? So what does that mean? Well, the maximum clearance is when you have the most space between the shaft and the hole. So think about that. When do you get the most space? Is it when the least material condition of the hole minus the least material condition of the shaft? You know the difference between the two? Or is it B? Where the maximum material condition of the hole minus the minimum material condition of the shaft is a number, right? Is the biggest number. So take a look at that. You want maximum clearance. So when is the space the biggest? So most of you are saying A. Okay, so least material condition of the hole, right? That means that's when the hole is the biggest. And least material condition of the shaft is when the shaft is the smallest. So that'll leave you the biggest gap. Okay, so that's maximum clearance. Okay, and you'll have to kind of remember these definitions. So study them. Now, minimum clearance, that's when the minimum amount of space exists. And it can be a negative number. Okay, so when you have force fits and things like that, that could be a negative number. And what that means is that the shaft is bigger than the hole. And that would be a material clearance allowance, right? So, and sometimes there was a gap. So let's see what you come up with here, which is what's the answer for the minimum clearance? A, B, or C? Okay, B. Everybody's saying B. So minimum material condition for the hole. That means the hole's the smallest. And minimum material condition for the shaft. I don't think so. Let's see. Okay, minimum material condition for the shaft. All right. So that's the minimum clearance that's allowed. All right, now for this one, what's the maximum clearance in the number? All right, you guys got it. Minimum clearance? Now we're cooking. It's a negative number, isn't it? All right, negative 0.02. All right. So remember that it can be a negative number. So do the math right. Don't throw away the sign. All right, we're going to skip that because you're still here, and we still have time. Goes a little faster online, I think. So maybe we can finish this chapter sooner than later. So we have different kinds of fits, and there's 4 different kinds. There's the clearance fit, the interference fit, the transition fit, and the line fit. And we're going to go through each one of these definitions. Okay, so what's a clearance fit? Well, the clearance fit, what that means is there's always a space. Okay, so if there's always a space, that means the minimum clearance is greater than 0. So remember your definition of minimum clearance, and there's a hint at the bottom. Okay, go ahead and put that in there. No, it's not a clearance fit, right? Because the minimum clearance is actually a negative number. What's an interference fit? Well, that means there's never a space. So the maximum clearance is always negative or 0. So that means it's always going to interfere. So you take a shaft out of a box of shafts you made that are within specification, and you take whatever you're going to, whatever has the hole in it, you take that out of the box, and those are all in spec, all the ones in the box. You're always going to have a tough time putting that rod into that hole, okay? That shaft into that hole. So that means there is never a space. Okay, so the maximum clearance is always less than 0 or equal to 0. Okay. Now we got a transition fit. What is that? Well, the maximum clearance is greater than 0 and the minimum clearance is less than 0. Okay, so it could slip a little bit, or it could not, it may not. Okay, so you have to calculate 2 things, the maximum and the minimum clearance. So is this a transition fit? Okay, and then this is a line fit definition. There is a space or a contact, okay? So that means it's gonna either slip in kind of easily, or it's gonna make contact, a little bit of contact. But it will never be negative. All right. So those slides you want to go over and maybe make some flashcards, right? Write it on one side, put the thing on the other side, and practice those, because you're going to have an online test. So you don't want to be flipping through definitions when you take your online test, because you will have some time limitations on that. Okay. So from everyday life, can you come up with an example of a clearance and interference fits? So let's do clearance first. When there's always a space. So what kind of an example from your house can you come up with? Okay, Legos. Is Legos always a space? Door, table. What part of a table? Okay, Nick, you got to turn your mic off.
Shut up. Retard.
Hey, turn off your mic.
No, you shut up. I'm doing something.
Where is he?
Suck my dick.
Well, that was inappropriate. Okay. All right. I apologize for that. I don't know who's doing that, but hopefully they won't come back. All right. Let's see. Curtain on a rod, outlets, USB connectors. Okay, let's see what we got here. A lock and key, a door and a door frame, right? You always want clearance there. Coin in a coin slot. So you get the idea. Curtain and a rod, yeah. All right. What about an interference? So remember that there is never a space. It's kind of a tricky one. Yeah, the hammer. Okay. All right. So the pin in a bicycle chain is an interference fit, right? It's loose until you put tension on it and it connects. And then there's a hinge pin, the pin in the hinge, right? There's clearance there, but when you start to rotate it, okay, you will get some interference in it that way. And then a wooden peg and a hammer toy, right? Goes in easy, and then they hammer it in more, and it gets stuck. All right. See how we're doing on time. About 20 minutes left. All right, now let's take a look at this example here and see if you guys can remember what we just went through. We have shaft limits, okay, from 1.498 to 1.500. And then we have hole limits, 1.503 to 1.505. So what do you think the basic size is? Any ideas? Yeah, 1.5. Okay. What about the type of fit? Oh, you got to remember all those definitions. Clearance. What's the definition of clearance? Let's see. Let's go to the definitions. Right? Minimum clearance is always greater than 0. Okay, so you always have a space. Now, what about the next one? What's the basic size for the second row? 0.75, okay. And what about the type of fit? No one's guessed yet. Ah, there we go. Interference. Very good. Okay, so the hole is always smaller than the shaft. Now it's going to get a little harder. So what would you say the basic size for the third row is? Okay, 375. What about the type of fit? Yeah, transition. That sounds reasonable. All right. Okay, basic size for the fourth. You should all get this right. 25. All right, 0.250. Perfect. And what type of fit? Now, you can also say quarter, right? That's good. Line fit. Very good. All right. So these are the kind of questions that you'll be quizzed on. Okay. So now you know how to do clearance fit, line fit, interference fit, transition fits. You kind of understand that. You probably have to practice that some more. Now you can start to transition over into things called running or sliding clearance fits. Okay, and that's a specification. Okay, and always think of the shaft and hole example, right? You've got running or sliding clearance, and that's intended to provide running performance with suitable lubrication, right? So we usually lubricate parts, okay, and then we want to have some clearance so that they can move, but you may not want them to move, you know, when they're going laterally, right, sliding this way. You may not want much slop in it, so it can't do the, it can't tilt. So you can specify the running or sliding clearance fit with an RC value. Okay. So there's an RC value where RC9 would be the loosest and RC1 would be the tightest. Okay. And that's how it works. So the bigger the number, the looser it is, and the smaller the number, the tighter it is. And then there are tables that help you understand how to machine that. So you could give, for example, a machinist a basic size, right? And then you can give them a running clearance fit specification, RC5. And then they'll know how to make the hole in the shaft based on that, okay, by looking it up on the table. Okay, and then they have locational fits, LC, LT, and LN. So LC is locational clearance fits, LT is locational transition, and LN is locational interference fits. So they're intended to determine only the location of the mating parts, okay? So there's some more examples we're gonna do later on. And then there's another set of standards called force fits. Okay, so that's where you want a specific pressure, right? A specific strain once the two parts are put together. So a lot of times if you're doing like a force fit, okay, or you're putting parts together that are at yield, what they'll often do is they'll heat up one part, like say the part with the hole in it, and it makes the hole bigger, and then they'll put the shaft in, and when the part that's been heated up cools down, that hole gets smaller, and it becomes a force fit, a really tight fit. Okay. All right, let's do a couple examples. We still have some time. So, like I said, I'm gonna, I can give you a basic size. So this is a 1/2 inch, and we want to make a fit that's RC8. So what are the limits for the hole in the shaft, right? So you go look it up in the tables, and they're given in your book. And then I think I give you some tables with the homework as well as attachments. So make sure you look at those. But the table looks something like this. Okay, let's go ahead and study this a little bit. We have nominal sizes on the left column. Okay, so remember the basic size is 0.5. So you'd go down that first column until you find where 0.5 would land. So that's in the 4th row. Okay, you can see If the nominal size or the basic size is between 0.40 and 0.71, you're on that row, right? So it is between those two. So now you go across, and we want you to make, or you want your machinist to make something with an RC8 fit. Okay, so the RCA fit class is the fourth column. So you look at where that column and the fourth row intersect, and that gives you your standard limits. So now that's a plus 0.28 and a 0, and then a minus, that's for the hole. Okay, and then for the shaft, it's a minus 3.5 and to a minus 5.1. And so those are in thousandths of an inch. Okay, so it's 3.5 is if you do thousandths of an inch, right? You would be at let's see, 0.0035 inches. So you move the decimal place 3 times, okay, to get thousandths. All right, so let's think about that, right? Your shaft is going to be 3.5 thousandths of an inch smaller. Let's see. This is an RC, yeah, running clearance 8. So this is an RC8. So the shaft's going to be 3.5 thousandths smaller than the basic size of 0.5 and down to 5.1 thousandths of an inch smaller than the base. Okay, so can you write the limits for the shaft based on what's on this slide? Can somebody put that in the text box? See if anybody gets this. No, no one's venturing for this? Okay, it's still a little confusing. All right, let's take a look at that. So I've highlighted that intersection point, okay, and the little image there. So the standard hole limits, okay, is plus 2.8 and 0. Those are in thousandths of an inch. Okay, the standard limits of the shaft is less than that amount in thousandths of an inch. So you have to subtract them. And that's what you get. So your hole will go from 0.50.
Matt,
Yeah?
shut your bitch ass up. Fuck you.
Oh my gosh.
No.
I wonder who this person is that keeps trying to get in. That's too bad. All right. They're hacking in. Okay, you get your hole limits there, right, by subtracting that out. And then you do the same with the shaft limits. And now you can kind of see, that it's a running clearance. Your shaft is always smaller than the hole, and RC8 is got a lot of I'm distracted here with what's going on. All right. Anyway, so from the table, you can find out, which way to go from your basic size, and then you can create your limits based on that. And that's what the machinist would do if you said you wanted an RC8 with a basic size or a nominal size of 0.5. That's how you would do it. So you have a lot of homework that makes you go look up tables and then come up with the limits. So you'll get a lot of practice at that with the homework. All right, I think I'm gonna stop at metric tolerances. We'll start there on Thursday. Go ahead and take a look at at the homework and then do the best you can.